This week's episodes were brought to you by Snoopy. Hey folks, Quillyteen here, and welcome to another episode of our Project MightySpud. This is our Unity project where we're making a full terrain generation engine for a planet. Now, if you were following the channel closely, you saw that I actually spent a full day programming for about 7 hours and recording about 3 hours of footage, previously working on part 9, well, part 9/10/ probably 11 or something like that. I was going to have to do a lot of editing to get a solid video out of that, and actually a lot of it was going to involve, like, sort of being a little unsure about certain things, occasionally taking some wrong turns, and while I do like to keep those in my videos generally speaking, I think it would have been too much on a topic that's already quite confusing. So I decided to start over the recording today, and as a bonus, I think I actually realized a simpler and more intuitive way to do one of the very, very critical steps of this process, and at the same time actually provide an important function that we are going to need desperately later on anyway. So I think this is going to be a huge win. Anyway, so here we are. What I've done is I have gone and made a variant of our map topography over here, where I just drew a black line down the middle of the equator to drop the terrain there, and then I used white text on our image to write some numbers and letters on here so that we can, it might be a little hard to see in the video here, but when we start generating our little terrain chunks, we will be able to get a very good sense that we are A, rendering the right area, B, the orientation is correct, we don't have things mirrored or anything like that, which would have been kind of odd. So that's going to be good for testing. Now, as we have established multiple times, including as a big part of Part 8, we cannot use a single piece of terrain to render the world. It's just not possible, and get something that feels appropriate. Like, everything's going to be distorted in some fashion. So what we want to do is have many little chunks, especially since what we actually want to do is we want to render this world very, very big, and generating a high enough res terrain so that the terrain feels right and also, be just span an entire planet isn't really possible to keep that all in Unity memory anyway. So we're going to be dividing the world up into little chunks, and that's what we're going to be working on today. So this chunk engine is going to make it more feasible to render the moon at a more realistic size. For gameplay reasons, you'll probably still want to go and scale things down by a factor of 10 or maybe even 100, just so that it doesn't actually take you 3 weeks to, walk all the way around a planet. But you still want it to be pretty big. So we're going to be working on that today. So what we're going to start off with first is we have to actually make a change in our dynamic terrain over here. Right now we have a single dynamic terrain object, and we have a single script over here to generate that chunk. And while technically you can sort of zoom in a little bit with the viewing rectangle, it is not in any way a useful function for us to use to describe what area of the world we're going to be drawing. So the first thing we're going to do, what I'm going to do is I'm just going to go ahead and disable the dynamic terrain over here. I'm going to leave it in here just because we're going to have these little, this little info about our current settings as a reference, which is going to be nice. But we're going to go and create a new script over here, and we're going to call this one Dynamic Terrain Master. So what the dynamic terrain master script is going to be responsible for doing, it's going to be responsible for knowing, say, where the player is coming out of orbit, where the player is landing on the planet, and then generating a certain amount of terrain chunks around that area. And this is not going to be what we're going to be working on immediately, but it will be responsible for tracking the player as the player moves around and spawning new terrain chunks in the direction the player is moving, as well as despawning terrain chunks that are too far away from the player to be relevant at that point. That's the dynamic terrain master's job. In addition to that, though, our dynamic terrain script over here, I'm just going to go and rename this to make it a little bit more clear. This is going to be a dynamic terrain chunk. So the dynamic terrain chunk is still going to be responsible for generating the actual terrain object, the actual terrain mesh, but only one chunk at a time. So I'm just going to be renaming that class to be a little clearer, as well as I'm going to rename this file over here. So that's good. So next we're going to create a new empty object in the world. I will center it just to make life a little bit more straightforward, although I think it doesn't matter one way or another for this. We're going to call this one the dynamic terrain master. And we're just going to go ahead and apply that script to over here. Excellent. And then we're going to go ahead and open that up. So we're going to start working on this. Obviously, we'll have to make some changes to the dynamic chunk generator for a few ways. One, it's going to have to get data from the master. And two, it's actually going to have to be rendering things mostly correct. There will be a few things we are likely going to leave outstanding in this process, and the idea being we're going to take another pass later to maybe fine-tune certain things, but it'll depend on a few things. So right now, our dynamic terrain master is not actually going to need an update function. Later on, it will, because it's going to be, again, probably responsible for tracking the player, or the player is going to send signals one way or another. We'll see. But for now, we don't need that. And really what we're going to have is we're going to have a big master function here that's going to be something like, I guess I will plan as a public, because it'll get triggered by other stuff later on. But it's going to be something like build from landing spot. Okay? We are going to take in some sort of landing spot. So we're going to get a spherical coordinate, which is going to be our landing spot. This is where the player has come down on this world, and we've got to make sure that our initial chunk of terrain is there, because that's where the player is trying to land. And so our start right now is simply going to call that, and we're going to call that using the, just like the 0 degrees, 0 degrees location. So we're going to be at the equator at the prime meridian. So we have to provide a new spherical coordinate. Spherical coordinate doesn't actually have a constructor, and it seems like we should probably make one. Here it's fine because it is going to default to 0, 0, but it seems perfectly reasonable for us to have one. Now, if you define a constructor, so in this case we'll have one that takes in a lat and a longitude, right? If you do this, that means there will no longer be an automatic default constructor, so we're going to have to make sure that we also have one that is just doing like that. And technically I don't have to do anything else because my floats are all going to get set appropriately, but just in case we decide to do, you know, a little bit more work in the constructor later on, what the default constructor is going to do, it's just going to call this secondary one and force these coordinates to be 0, 0. And all we're doing is we're setting latitude to be equal to lat and the longitude to be equal to this past longitude, and there we go. That's all we have there. So really over here, just to make it explicit what's happening, is we are landing at the equator at the prime meridian. It's going to make it easiest to start our testing at that point, and then we'll, you know, try different combinations at that point. Okay, so we're going to be doing a build by landing spot there. And what we're really going to be doing as our first step is we're going to be making a single chunk. So really, we're going to want another function here. This one definitely won't be public. This will be something like build chunk. There we go. Actually, literally my keyboard is slightly too far to the left from where I normally am sitting. So this is going to take in some sort of information. There's definitely going to have to be something over here, okay, to build a single chunk. But right now, the way this is going to work is we are going to create a new game object, right? There's going to be some sort of game object, which is going to have a component on it. And that component is going to be the dynamic terrain chunk component over here. And we are, I guess we're going to want to keep a copy of that. So dynamic, I guess if I put a space in here, I think it would have the, there we go, auto completion working. We're going to call this the DTC. And keep a copy of that. That way we can set the DTC dot, oh yeah, the height map texture has to be passed. Yeah, so, okay. We have to tell the dynamic terrain chunk what the height map texture is, as well as we're going to have to make sure to put in the splats, right? Because you have to remember the old dynamic terrain over here, which is generating a single chunk, needs to know what our height map is. We'll need to know, I guess, what our structure map is. Not that we've implemented it yet, but we've got a placeholder, as well as what our list of splats are, because it's doing like the cliffiness and stuff, right? Which is still going to be true. Plus, there'll probably be other details later on. Viewing triangle is going to go away completely. It's irrelevant. But what this means is in our master is going to have to know those things as well. So it's going to have a public reference to a, well, I guess I could just copy from the chunk over here just to make sure that everything matches 100%. Basically, our terrain master is going to need all of these things. Like that. And we want to go and make sure that gets populated. Semicolon expected? Oh. There we go. Comment that out. Just for now. Assign the value, expression is a type, but wait. Right. Let me just comment that out. Yes. You can't just call this constructor like that. We can do it slightly differently, but let's just comment that out for now. Okay, we are golden here, which is good. So now what we can do is in our dynamic terrain master, we can say, okay, your height map structure is this. The structure map we're ignoring for now. Your splats, there are going to be 2 of them. We have, what's the order? Dynamic terrain was the ground 2 and then moon cliff. Okay, so we have ground 2 and then moon cliff goes in there. And our sizes, we set these to 150. Which sounds fine. Okay, so now that we've got that, we can actually get rid of this old dynamic terrain. I just kept it around so that we'd remember what those values were. That's all. So we can get rid of that. Excellent. So dynamic terrain master has this info, which is good. So then what we're going to do is right over here. So your height map texture is equal to this dot height map texture, DTC dot structure map. Again, we don't use this yet, but at some point we will. Structure map texture. And the DTC.splats is going to be equal to this dot splats. And I believe this will give us an error. Yeah, so right now, the splats is an array of splat data, right? And splat data is a structure, well, it's a class that we define here in Dynamic Terrain Master, as well as here in Dynamic Terrain Chunks. This is Dynamic Terrain Chunk dot splat data, and this is dynamic terrain master dot splat data, and C# treats them as completely different classes that have absolutely nothing to do with each other, which is pretty correct. So we just have to define splat data one place and use it sort of like globally. Now there's 2 ways you could do it. First of all, in dynamic terrain chunk, I could go and just cut that out. That's fine, and then just say, yeah, this is dynamic terrain master dot splat data. Then all of a sudden everything would be okay. But I think, just to make our life a little less annoying, not that it really matters one way or another, is I'm just going to go and take this definition here of the splat data class, and I'm just going to move it outside of dynamic terrain master. So now it's just going to be a generic global class called splat data, which can be addressed anywhere. We can put it in a separate file. We can do different things. I think for now it's going to be fine there, and that's good. So now that should eliminate that error. Excellent. Good. Wonderful. So now we've gone ahead and we've created a new game object. We've applied dynamic terrain chunk to it. We have passed some information to it. And so if we play right now, all we have in the game is a single dynamic terrain master, which on start is going to call build from landing spot, which is then just going to get called build chunk, which creates a new game object, which applies a component to it. So if I hit play, are we back to the old terrain? Same as before? Hey, yes we are. So it's got this new game object in here, which is our terrain. Lovely. Again, this terrain is still currently generating an entire chunk, but that's okay. We'll get to the next step. So what will be the next step? Well, the next step is obviously we want the chunk to only be a certain area. And so we have to give some thought about how we're going to describe that area. Well, as discussed in the last episode, each one of these chunks is basically going to be at a certain position in the world, right? Obviously. Where's my Photoshop? Excellent. It's time for scribbles, guys. I know it's everyone's favorite. What I want to do first is just give a little white background there. Go to the next layer. There we go. And we'll just use our brush. Look, lovely. Okay. So again, let's imagine in our world that this is the prime meridian. This is the equator over here, and the rest is somewhere off away. This is a little zoomed in. So what we're doing is we're generating a chunk here. The first chunk I'm going to generate is going to be at that landing spot, right? So that's the 0 degrees right over there. So if we zoom in, right, and just switch to impact is fine. That's going to be way too big though. Let's go to a tiny little font here, 0 0. Yeah, probably bigger than that. 16? Okay, that's not too bad. So there's our 0 0 point over there. And at some point, what we have to determine is how big are these squares going to be. Now, there's how big has kind of 2 meanings in a sense, right? There's the question of how much Unity world space is this terrain chunk going to take up, but also how many sort of degrees of rotation does this represent? Now, of course, those are linked, right? Because in theory, assuming you're going for a fixed scale, a 1-to-1 scale, then how many degrees in size of the world, right? 360 degrees to go all the way around the equator. How many degrees wide this is also going to tell you kind of how many kilometers this is. But we are going to have some sort of scaling factor. So what we're going to do, just just for now, without thinking too much about the scaling, we're going to generate this chunk to be, we're still going to use our old numbers, which is like 1024 by 1024. Actually, right now, it's twice as wide as it is tall, but we're going to be changing that because we're going to be using square chunks over here. So it's going to be about 1 kilometer wide. And independent of that, we're going to choose how many degrees that represents, which if you go from one to the other, it tells you what our scaling is going to be. And our scaling is going to be very aggressive. I want to, for testing, I want quite a large one for our very first area over here, because that will let us see multiple letters and numbers at a time in my testing texture, make it easy to see what's going on. So what I'm going to do is I'm going to make this like 20 degrees wide, which means that over here, we're going to be looking at a sort of longitude, latitude of -20, like negative numbers is further north, and -10, because negative numbers are further west. This is going to be -10, 10. This is going to be 10, 10. And over here is going to be -10, 10. Okay? So those are going to be the starting latitude and longitude. And what's really important, though, is that our next tile over, remember that if we're looking at this flat, this is one of those areas where your perception gets all screwed up, right? Is if you're looking at this flat, then these, over here, make this a new layer, these longitude markers really seem, as you go further out, they really start to seem to do this curving thing, right? Because our orientation, our map, everything is bizarre and wonky and not exactly how you expect. So these coordinates don't represent latitude and longitude anymore, but rather at first it does. Technically for the first piece, 0, 0 it is, because what we're going to do is we're going to sort of take this line which goes through the center of the world. We're going to rotate it 10 degrees this way to get that information. And that's going to happen to work for the first time. But after that, it all sort of starts to break down, because what we're going to do for our next chunk is we're just going to tell it its center coordinates, which again, the center coordinates for the next chunk will be, I guess it'll be 2020, right? 2020. And then we're just going to rotate up and down and all these sort of things. And as you get further and further, remember that we're going to be going up over here. We're going to be making chunks this way. And at a certain point, you're going to end up with this chunk where it's crossing multiple longitude lines that are coming in like this. So clearly, this angle here. So at this point, we're going to be at, I guess this is going to be the 80-80 mark. Yeah, that actually makes perfect sense. 80-80 over here is going to be the center. And then we're going to be rotating 10 degrees up over here. So you're going to imagine that this is going to, or not 80, 80, sorry, it's going to be 0, 80. So this part over here is going to be 10, 90 as a rotation that represents this. But this has nothing to do with latitude and longitude anymore. Because really, at this point, you're actually almost like south. It's going to be weird. Anyway. I know I'm probably overcomplicating things as is. But the point is, to describe a chunk, all we have to know are really 3 things. We have to know what is the rotation, there you go, rotation that describes the center. This is going to be a quaternion. And then how many degrees wide is the chunk? And also, how much world space wide is the chunk. Those are really the only 3 things we'll need to describe a chunk, which is kind of nice. So we are going to, in our build chunk here, well, what we're going to have a few things. We're going to have, I think what I'm going to do is have a variable here, which will probably be a public later on. But for now, we'll just make it a private, because it'll make it a little easier to babysit. And we're going to call this something like degrees per chunk. Actually, instead of going with 20 to start off with, let's start off with 10. If that's not big enough, we'll make it bigger. Now, if we chose a really big value, like say 90, then we would be generating a chunk that is, actually, I guess if we went 180, this would be a chunk that would go from the North Pole to the South Pole, centered at the equator. And obviously, at that point, our chunk would not be accurately representing the terrain, because it would not be dealing with, well, you get all the weird distortion and things like that just look bizarre. So that's not what we're going for. But it just so happens, as long as you keep your chunks small and sort of kind of correct on every one, while making sure that the chunks get stitched together properly at the edges so that they're seamless, you get all these tiny little micro distortions along the way that all look fine, because at small scales, you can treat everything as if it were parallel, and we can keep sort of fixing things along the way. So everything will always look parallel and undistorted, but accurate. Assuming we did our job correctly, which is a good chance that we won't, but you know, a boy can dream, right? So we're going to do that. And so there's degrees per chunk, and I suppose there's going to be some sort of value for like world units per chunk, which we're going to start with like 1024 is going to be the physical size of our object. And there's no reason this has to be power of 2 other than the fact that it feels good to work in powers of 2. So we're going to have that. That's going to be fine. And yeah, and then other than that, we're going to be working with orientation. So when we build a chunk, what we really have to go and pass to it at this point is, for this chunk, we don't have to pass degrees per chunk or world units per chunk, because we can, you know, set some sort of value here for that. That's okay. But for this particular chunk, because we're going to be calling build chunk many times per loop, and so for each one of these, they will individually be represented by a different rotation, as well as they'll be individually represented by a different position in the world. So they're just going to be offset by this amount. That's all, you know, in X or Z, right? Because the Y's will always be just 0 because we're keeping things flat. So we're going to have to pass that kind of data over there. Now, the first one is going to be very simple. We're really just going to be passing the original landing spot. And the position is just going to be vector 3.0 in the world space. That's going to be fine. And remember that our landing spot is actually going to be at the equator, 0 latitude, 0 longitude, which now, because of the way that we're working things, will represent exactly 0 rotation. Yeah, so I can't just pass landing spot, derp derp. I have to convert landing spot into a rotation, which I don't think we have a helper for that, right? We have the ability to go from a transform to a spherical coordinate. We have the ability to go from a spherical coordinate to a UV, but what we really need is we actually might need them to go both ways. I think we do. I think we're going to need something that's spherical to rotation. So we're going to take in a spherical coordinate, and we're going to return a quaternion, which is actually going to be really easy, because the quaternion is literally just going to be using these Eulers here, where the latitude represent rotation around the x-axis. So the higher the latitude, or, well, as the latitude goes negative, it actually goes towards North Pole. But that's rotation of the x-axis that goes through there. Yes. I think that's true. Whatever, let's just go with it. Latitude. And then the longitude describes a rotation through the polar axis, which is the y-axis over here. So sphere coordinate dot longitude, and there's no rotation around the z-axis here. Although, that's the thing, there's no rotation around the z-axis when we are reading from the latitude and longitude. But the interesting thing is our individual terrain chunks totally could be rotated around here. Now, we wouldn't actually rotate the terrain chunk itself. We actually can't, but it can basically, and we'll probably test this later on, there's no reason that we can't imagine that this is actually sideways, and a rotation, our actual chunk, when we look down on it, could have a sideways 2. You know, if it's on the 2 spot, the 2 could be sideways. There's no reason that, you know, and therefore north would be facing off towards upper right. No reason we can't just support that, so that's going to be okay. All right, so we're going to do this. I think we had a bit of an error there, but we're going to resolve that in a second. And I think it would also be something where we're going to want to be able to, not sphere collider, spherical coordinate. We're going to want to be able to go take from a rotation to spherical as well. So we take in a quaternion that represents a rotation, and we want to be able to go to a spherical coordinate. So that's going to be return a new spherical coordinate, which is going to use the rotation dot Euler angles. And so we're just inverting what we had before. The x is going to get used as latitude. The rotation dot Euler angle dot y is going to be used as longitude. And we ignore the z component, because we don't care how, like, sort of twisted. The z component will represent sort of how our character is facing, or how our terrain is facing, right? X and Y is going to be our position on the Earth, and the Z represents, you know, are we facing north, south, or somewhere sideways like that. So for this particular step, we don't need that. And that means we can also do an intermediary step over here, which can be quite handy, which is going to be, because we can go from spherical to UV, so we could do something like returns a vector 2, so we can go from a rotation to UV coordinates. So it takes in a quaternion. You know what? Let's just call these rotation. I think I'll feel a little bit better if we use a longer form word over here. There we go. And this is just going to return the result from, it's going to be just calling spherical to UV, which means then it just takes rotation to UV. So rotation to coord. So it takes the rotation, the quaternion, turns it into a spherical object. Turns into a spherical coordinate, which then passes the spherical coordinate to the thing that generates the UVs. Also, I'm pretty sure I addressed the fact that this -1 is going to be wrong. I'm going to leave it in for now. The 1 minus is probably wrong. We had that in because of some other thing we're doing that, but we're probably going to be removing that because if we look at spherical coordinates, we say that 0 is the left edge, right, in our rotation. So if the longitude is 0, then we should be returning a UV of 0 to represent the left edge of the image. It mostly comes down to whether or not we're doing some rotation somewhere else. But you know what? We'll correct it somewhere else. I'm just going to remove this. That way, when we have 0 degrees, we are correctly going to return a U index of 0. So 0 longitude is a U index of 0, which I think is going to make things a lot happier. I realize our current dynamic terrain chunk engine will now result in us getting a mirror image instead of what we want, but I think it's going to be okay. So do we still have errors over here? Yeah, we do. Best overload match has some mismatches. Oh, right, yeah, because here we're trying to pass the spherical coordinate instead of what we want. So let's go ahead and do a quaternion called rotation. Sure, rotation. What the hell? Which is going to be set from our chord helper dot spherical to rotation. There we go. So we're going to pass the rotation, and you know what? I'm going to call this rotation, and I'm going to call this one position. There. Excellent. Good. More letters are more better, right? Sure, something like that. Okay, so we've got that, we've got that, we've got that. Good. We are passing this information, which is fine, but now we need to describe the area that the chunk is going to be rendering. Now, this is one of the things I've changed from my initial work on episode 9. Originally, what I was doing is I was describing something that I was calling like terrain position data or something like that, which was actually a custom class which really passed along. It passed along what? Oh, it passed along the rotation. So it had like one component in this class that was, you know, the rot or whatever. But it also had a quad set, an array of vectors, which were the UV quads. There were 4 of them. And what this was for was, where's my Photoshops? What this was for was something like this. Let's make a new image here. Let's go and fill it with white, and then make a new layer, and then switch to black in our brush. What this is for was this. We had in our world map, right? So let's say over here, this is our map of the moon, right? It's got some craters and stuff. Very exciting. When we get down to the pole, the chunk that represents the area at the pole, right? So we have some terrain over here that represent. This is our terrain object that represents the North Pole. In our actual texture map, remember over here, if we bring up the texture and you can look at it here, the pole is really distorted and stretched, which means that the area of the image we're going to use to render our height map, we don't want this area distorted. We don't want it to look like all stretched like that. Doesn't make any sense. We want all the bits that are supposed to be at the North Pole to be, you know, correctly undistorted, which means that where we're going to be reading, the pixels we're going to read from the image that represents this square terrain chunk is actually going to be an area like this. It's going to be, we're going to read from a wider area there, and then it's going to get sort of squooshed in over here, and that will correct that distortion. Okay, so one thing you can do when you're building your terrain chunks is really, you could pass it the 4 spots on the corners here. We can tell what the UV coordinates are of these things, which would basically mean we'd end up with something which was like, this would have like an x of 0.4. and a y component of, I don't know, whatever, 0.9. And then down here, what we end up with is an x component of something more like 0.3, and a y component at this point we'd be at like 1.0, right? Assuming we were squished right along the bottom of the screen. So here again, our terrain chunks have to be square, but what pixel we read from doesn't have to be. So we end up with this weird parallelogram, which again brings you to the strange question of, well, okay, that's fine, but what does the next square over here, the next terrain chunk, where the hell are we reading from for that? And you're going to say, well, isn't it going to be weird and wrong that we're going to be reading from something that looks like we'd sort of be reading something like this, which would be it's not square. This is not a 90-degree corner, and this is because this is going to be more narrow. And that doesn't make any sense. Except it does, because you have to remember, we're using a flat representation here of a round world. So these corners, these angles will never meet up, because you have to remember very carefully that, let's assume this part over here has come right down the prime meridian. And remember that the bottom part here, this is the North Pole, right? We're at the North Pole. So north is this way. This is because we're at the South Pole. But if this is the South Pole, then north is also this way and also this way. And so this is going north, which means that, and remember where all the other longitudes come out of, right? Over here, you get this. So it means that this direction here is going to be north and mostly west, actually. Which makes, if I'd drawn this better, actually, it would be more like, the split would be something like this, right? Right? So this is actually the sort of parallelogram. Well, no, it's not parallelogram. I don't know what you would call this, but this shape, right? And if you think about the angle this is going north, but mostly west. Which is exactly what we'd be describing here. North, but mostly west, really, as we cross over. So this is why everything is going to be bizarre. If you draw on if we overlapped on our terrain height, the areas that we're reading from for each one of these square textures, we end up with things that go off at weird angles. We end up with things that are not square, and everything feels really bizarre, and yet it is correct. Now, the one issue starts to become, what this next square, what does it represent, or how do we read from that? But again, it sort of turns out to be okay. Again, you end up with something that's definitely not square. You know, again, I'm sort of butchering everything, but accurate. Now, if we were making these squares this big, at some point, I think things would definitely fall apart, where you were definitely having to draw squares that wouldn't make sense anymore, and that might overlap. But as long as you keep things tiny, or relatively small, you'll never end up with like really bizarre distortions. Again, it becomes, the degenerate case is if your square was so big that it was like this big, well then it doesn't make sense, because really what you have to do is you have to pinch things in, right? All of a sudden, like this. And so, well, no, you could sort of maybe, I don't know. It doesn't really work out, but sort of kind of does. But anyway, God, this is such a complicated topic. I'm finally feeling like I'm getting it. I just don't know if I'm getting enough to explain it in a useful way. Anyway, the point was, in my first approach, what I was doing is I was telling the squares what all these four corners were. Because it was pretty easy to calculate, and I was saying, oh, okay, well then we'll just pass those four corners. And then in my dynamic terrain chunk code, what I was doing, and here, what I'll do is I'll actually paste in the old bit of code here. Hold on a sec, which was, now we're not going to do this time, but for the sake of argument, what I had was a function. Here we go. UVs from quads. So in my dynamic terrain chunk, as I had this function here, that, of course, you can't paste because MonoDevelop is terrible, and apparently I've got some non-Unicode characters somewhere along the way. Oh, that's probably just new lines. Okay, what I had was this. So again, we had that array of the four quads. So the quads in this case was just representing each corner of the image over here, right? It was the UV index of these things. So it was that 0.4, 0.9, 0.3, 0.1, and so on and so forth, that described this weird, shape that was like this. Okay, this shape here. So each one of these corners, this was 0, 1, 2, 3 in the index. Okay, and so we had that, and then this is the position. This was the position on the actual terrain chunk that we were drawing, which was to say this would be 0, 0, this would be 1, 1, right in the middle would be 0.5, 0.5, for example. And then what I would do is simple, is for each one of the corners, is I would figure out how much of a contribution would happen. Because we're looking to find out, this is supposed to return the UV coordinates of the correct pixel to use for the height at this particular position in the terrain. And it's very easy to understand these drawings, super easy to understand. If I clear this out, right, make a new layer over here. If we have, again, we have got our terrain, this is our terrain square over here. Okay, it's terrain rectangle, but pretend it's square. And then we have the area that we're actually reading from the texture over here. If our position it was at 0, 0, then obviously we only want to use this coordinate, which is our 0.3, 0.9. Here, I'll just care about the x component, right? And over here we had, say, 0.5, and then here we had 0.2, and 0.6, okay? So only looking at the x component of these things, right? So if you're at 0, 0, you're only going to use this, and you're not going to care about any of the others. Same thing if you're at the bottom right corner, the 1, 1 value, you're only going to use the 0.6. So the correct pixel to use would be the 0.6 pixel over here. If you're in the top, then you ignore both bottom bits, and you just take, you just do the math between these two. So in this case, you'd be using 0.4 coordinate on the image to read in your image data. Same thing anywhere along this line was basically just a proportional change from here to here, right? That was fine. And same thing at the bottom would just be the bottom bit here. And in the middle, what you're really doing is you're taking the average, the exact average between all these. Each one of these would be contributing a quarter to the data. So one way to think about it would be 0.2 plus 0.3 is 0.5. Another 0.5 is 1. The 0.6 gets you to 1.3. So divide 1.3 by a quarter, and it turns out that that would be the correct x for right over here. Ish. Something. I think I may have screwed up. Anyway, something like that. Okay? So all this function was doing was doing exactly that for each one of these corners, but of course we were paying attention to the y component and doing different things like that, is we would add these together. So the most any one of these would be, all of these, if you added in the distance 0, 1, 2, 3, add them together, it would always come out to a value of 1. And so we're just lerping that value from the actual quad value versus 0 based on the individual distances. So the returned UV would always be the correct pixel. So that was a way of doing it before, and it works beautifully. Except the thing is, it also required this really weird function to try to deal with quads when you went over a seam. What do I mean by that? Well, it's really easy to imagine that if we're working near the edge of the image, right? If we're working near the prime meridian, right, which is this left edge over here, or, working near the right edge over here. But if we ended up with a square that went over, you could very easily end up in a situation where the correct UVs for your rectangle here were something like, well, this has an X rating of 0.9, and this one is a 0.1, because the equator, or not the equator, the prime meridian goes down here, right? So then you get this weird slice, and if you're trying to lerp from one to the other, it doesn't work because it's trying to lerp backwards. It's going to go 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.2, 0.1. And then your image would be mirrored, right? Because you'd be going the wrong way around through your texture. And not only that, you'd be basically rendering the entire world over here instead of the tiny little slice that goes from 0.9 to 1 and then from 1 to 0.2. So you're supposed to get, 0.2 worth of content in this area, but instead you were getting 0.8 worth of content backwards. So everything was wrong. And the same thing will happen as well if we were at a pole, because there'd be this split over here, this polar split, where if we were looking at the y component, things would be inverted in the same way. So what it's having to do is like correct things where instead of going from, say, 0.9 to 0.1, you go from 0.9 to 1.1. This correctly loops in your texture, which is fine, and again ensures that the sort of amount of space used here is 0.2 worth of space. And that's correct, but it gets even worse than that because it's entirely possible, remember, that how we read from the texture isn't straight. You can end up with a situation where the split is here. So one corner is off, so you have to check for that. And even more confusing is you could end up with a case where two corners are off, but in different ways, right? Because this is the prime meridian, this is the split at the poles, so everything gets a little wonky. So you have to sort of correct for all this a little bit. Our new approach is going to be able to avoid that. And as a bonus, one of the things that's going to have to happen in the game is at some point, our character is going to be here. Our character is here, and we're going to want to know, hey, what's my longitude and latitude over here? So we're going to need some sort of ability to quickly determine, based on your position on our terrain chunk, this spot right here, what latitude and longitude is that? Well, the nice thing is, if we've got a way to determine what the latitude and longitude of this spot is, we have a function that takes latitude and longitude, our spherical coordinates, and gives us a UV. Now, all of a sudden, we don't need these quads anymore, because at any point in our texture, I can say, okay, listen, I'm trying to generate my height map right now. I'm starting here, then here, then here. And for each one of these points, right? So we're here at this point. Okay, I'm here. What is the correct UV coordinates of the texture right over here? Well, we can find that out if I can say, I'm here. What is the latitude and longitude of this spot here? Oh, excellent. I can get the UV from that, which means I can get the right pixel. So what we need is we need to implement a system such that for no matter where we are on this texture, we can find out in real time what our latitude and longitude is there. Well, that's actually not too hard to find out, as it turns out. Because first of all, the center, we're using the center of our terrain is coming in from that rotation aspect, right? So the center over here is our rotation. If we go back, okay, so I'm going to get rid of this UV from quads function completely. We're not using that. In our terrain master, we're building a chunk with a certain rotation as we go around. And we can go from rotation to latitude and longitude. And that's going to be the center point. So in our terrain chunk, what I'm going to do is this, right? This is our old dynamic terrain class. We're going to remove, first of all, viewing rectangle, because we're not using that. We're also not using height map texture scaling, we're using that. So we're not using the viewing rectangle, which I don't think will even generate any kind of error, because I think we're literally not using it. No. Okay. But what we're going to have is we're going to have a public quaternion that represents like this chunk's rotation. Maybe I'll call it that. I'm going to call it chunk rotation. Okay? Like that. And so when our master generates this chunk, one of the things we're going to tell the chunk is, hey, your chunk rotation is equal to this. So now the chunk knows this is the rotation that represents the point in the center. Sorry, would you prefer the American spelling of center for this? Probably. The center, that represents the point in the center of this terrain chunk. Reminder, you can easily convert this to a spherical coordinate, i.e. Lat longitude, right? By just using the X and the Y. But this is quite important because the Z component of this is going to be important because we need to know what our orientation is. Because remember, in our terrain chunk, we are, first of all, very confusingly, our terrain is described as having X and Y coordinates. But in fact, the Y coordinates of the terrain data actually represents movement along the Z axis in unity space, right? Because the Y component of the terrain data doesn't actually represent height, which is what the world space Y coordinate is. So it might actually be helpful in a weird way to describe three different sets of coordinates. Because what we could have, if we bring this back to say here, right? We are already referring to this as our U and V. UV represents the point on the texture we're reading from. And maybe in our terrain here, this is our terrain object, while internally it uses X and Y, which actually again in world space refers to X and Z space, because height is Y. Not only that, but it doesn't map, this is not necessarily north, right? North could be this way. So there's this really weird mismatch. It's like, should we refer to this as like A and B or something like that? I don't know. It's terrain X and Y, which has nothing to do with one or the other. Because confusion and awesome. Okay, anyway. Anyway, the point was that the Z component of the chunk rotation will actually be your instruction as to where north might be. Well, no, that's not true either. God! This is so fun. Okay, for different values of fun. So if we want, so you can use this chunk rotation to know for sure what the latitude and longitude of our center point is, right? So I said what we need is a function that says at any point along here, so let's say point here, we need to know what the latitude and longitude is there. Now, for the center, that's great, because we can use the rotation exactly. But over here, we don't know what the latitude and longitude is here unless we know how many degrees of rotation are involved here. Right? Because here's the thing. If this is, assuming everything is square, assuming we start at 0, 0, and assuming that we are currently working with each one of these chunks is what did I say, 10 degrees wide, right? In our master, we're going to work with 10 degrees per chunk. So that's the total width, which means that from here to here is 5 degrees. And so if we are positioned right here, then we know that we can describe a rotation as being 5 degrees towards the right, or that might be negative 5 degrees or something. I don't know. We'll deal with that next. But that's pretty fine. So it's some percentage of a rotation over here, which we can easily do with a quaternion. So the point is that the degrees per chunk, we have to pass it over to our chunk information. Now, it's only going to use this for one thing. Degrees per chunk is used to determine the rotation, or lat long even, or spherical coordinate, because we can convert from one to the other, or spherical coordinate of any point on our terrain. This can be used to tell the player what her lat long is, but also we can get UV information from this. So we'll in fact be using this as information to render our terrain properly. Okay. You follow that? Hopefully. All right, so over here, so we don't need the quads anymore because we're going to be able to generate those on the fly in a very, very cool way. I mean, maybe it'll turn out that that it actually is faster to use the old function, like just in terms of the math. And what we could do is we could just, generate those and cache those over here if we need to. But the thing that's nice about this is we will be able to get the correct UV on the fly, which means we no longer have to worry at all. This is a huge win. We don't have to worry at all anymore of the situation where we end up with a seam, because we're no longer lerping from one number to another. So there's a seam, doesn't matter. So we're starting here, we're going to do a rotation from here, we're going to convert that rotation to a UV index at that spot. Makes no difference about the seams whatsoever, which should dramatically simplify our code and make it a lot more reliable. All right. So we've already gone on for 47 minutes. I know we haven't done much coding, but hopefully we're continuing to effectively make a case about how we're going to move forward. I think if we run this right now, we basically get, well, we get exactly what the same was before, because we're passing some information to our dynamic chunk system, but that's it. Because we did remove that negative from our chord helper, we are getting a mirror image over here that's no longer matching what we're looking for. Yeah, we're mirrored along the XY axis, but I think that actually represented a bug in our dynamic terrain chunk code more than anything else. Over here, we should, yeah, see how we were doing this 1 minus here? So we had the 1 minus here, and as a result, we had to do a 1 minus here. So 1 was a result of an earlier bug that we then sort of continue to inherit. So if I remove that, we once again have the world the right way around. And we can tell that because we can actually see our letters, A, B, C, D, E, F, G, H, I. It's a little hard to see probably on the YouTube, but it's there. It's the right way around. We are correctly rendering the world. So we actually have already improved something, even though all this code is going to go away. Because, again, this code here, well, it's funny because we're already using, like, the spherical to UV, right? We want to know the spherical coordinates. Yeah. Actually, we already have that in here. What needs to be changed, so X pause and Y pause is our position on the terrain, where 0x is the left side of this terrain chunk, and 1 is the right side of this terrain chunk. So from those, we're converting that to spherical coordinates, okay? But right now, we're assuming that we're generating the entire world. So all we have to do is, instead of saying, oh, we're generating the entire world, instead we have to figure out we know what our center point is, right? We know what our center point is, and we know the total width. So we know what our left edge is and our right edge is. So we're just going to use that left edge information over here and our width, which will give us latitude and longitude. And then all of a sudden, we've got this working okay. Like, it's going to be so much simpler than the approach I took before. It's just incredible. It's just, oh, it's going to be so much win. See you next time, folks. Bye-bye. Thank you to all our February Patreon supporters, including these mic check supporters. We've got Yukofin, Snoopy, TRB, Pavel Zdanov, Drazian, Gavin Power, Jan Torivel, Michael McClintock, Aaron Toyvson, Craig Mortel, the not-so-evil engineer, Julien Auger-Lafont, Maris Vold, Speedysant, Steven Stager, Valiant Cake Fiend, Wes Oldenboiving, Jason Yanity, Stephen Bonnerman, Kale the Quick, Neil, Blakey, Milner, and absolutely everyone who's watched, shared, favorited, and subscribed. Thank you so much for making this possible.